Hello again, everyone. We're going to be talking a little bit more today about gravity and motion, and I'm going to ask that you kind of revise those prompts that you started with the other day. I don't want you to erase what you've already written, but as you're watching this video and after you're done with this video, I want you to go back to those prompts and I want you to add and revise answers. You can add them in a different color so that we can see your previous thinking and your thinking after watching this video. All right? So we're going to start with talking about where do you find gravity? That was one of the 4 prompts you did yesterday. Where do you find gravity? And to help us answer this question, we're going to turn to Sir Isaac Newton. Good old Newton, he was a very intelligent man, and as the story goes, he saw an apple fall from a tree, and that helped him solve all the mysteries of the universe. Go figure. According to him, he saw the apple fall, and that got him thinking about why the moon orbits the Earth. Right? So he thought that every object in the universe, anything that contains matter and has a mass, is attracted to other objects, has this attraction. This he called the law of universal gravitation. And because everything is attracted to everything else, that's why we have gravity. Right? So really, there should be gravity everywhere in the universe, according to this law of universal gravitation. So when you answer this prompt, take a look at what you thought might have gravity, what you thought might not, right? And you can kind of revise it because now we know anything that has mass is going to have gravity, so you can find it everywhere. All right, so now that we know where you can find gravity, that it's everywhere, is all gravity created equal? Right? So we ask ourselves the question, is gravity the same everywhere? And it kind of depends on 2 things. Right? So the attraction, the strength of the force of gravity depends on the mass of the object. Right? The bigger the object, the stronger the force of gravity. That explains why the sun attracts all the planets in our solar system. They all orbit around the sun. The sun is the biggest object in our solar system, and it has the most mass, so it has the most gravitational force. The other thing that impacts gravitational force is distance. You can kind of think of this as when you hold 2 magnets together, the further and further away you hold them, the less they're going to be attracted and pulled together. Another way to put this is, so the Earth has a gravitational force, the further and further away you get from the Earth, your weight is actually going to change, because weight is a measure of gravitational force. If you weigh 100 pounds at the surface of the Earth, if you get, let's say, 24,000 miles away, you're only going to weigh about 2 pounds. Doesn't mean your mass changes. You're still made up of the same amount of stuff, but the force of gravity is not going to be as strong between you and the Earth. So your actual weight, if you were to step on a scale, is going to be a lot less. So to answer our prompt question, we could really say that planet B, because it has more mass and is larger, is going to have more gravitational pull than planet A. So if you were trying to launch a rocket off of it, it's going to be a lot harder to launch that rocket than it would be off of planet A. There's going to be more gravitational force pulling that rocket down. All right, so if gravity is everywhere, that kind of poses the question, why is it that astronauts, let's say astronauts that are floating in a space station that orbits the Earth, why is it that they seem like they're gravity-free? They're floating. And the answer to this is kind of the same reason that you feel like you're floating when you're on a roller coaster ride or when you're going up and down in an elevator. Right? It's a feeling of weightlessness. It's not actual weightlessness. They're not actually experiencing zero gravity. If they were experiencing zero gravity, they would just float off into space. They wouldn't be orbiting the Earth. Right? So there's still a gravitational pull holding them so that they can orbit the Earth. They're still experiencing some gravity. What they're feeling is that they no longer have a force pushing back at them. You can kind of think of when you're going up in an elevator, you start to feel heavier, right? Because the floor is pushing on you to help you fight against gravity, pushing up. And then as soon as you start to go down in the elevator, you start to feel lighter. or down on a roller coaster. You feel lighter. Your stomach almost leaps up into your chest. Right? That's a feeling of zero gravity, a feeling of lightness. You're not actually lighter. The gravity hasn't changed. You're still on Earth. You're still experiencing the same amount of gravity, but you're feeling lighter and you're feeling like you're floating. In order to prepare to go out into space, they'll actually take astronauts up on these planes and they'll go straight up and then they'll fall straight down into free fall. And you can see they're floating here. They're still on Earth. They still have gravity acting on them, but they look and feel like they're free of gravity. That's free fall. All right, so we've taken a look at that. In this prompt, we're faced with the question, is the moon falling? Right? And we just talked about how if you're orbiting the Earth, right, you are experiencing some gravity, otherwise you'd go floating off into space. So our two prompt people here, if we look at Maribel, who says the moon is falling toward the Earth because of gravity, we look at Isaac, the moon can't fall toward Earth because there's no gravity in space. Well, we already just kind of answered that there is gravity in space, right? The moon has to be experiencing a gravitational pull with the Earth, otherwise it wouldn't be here. It'd be floating off into outer space. So we know that Isaac is probably not correct here. But why is it that the moon doesn't crash into the Earth? That's something we kind of have to address here. So you can think of gravity as something called a centripetal force. That's a force that's moving or tending to move towards the center, right? So it's this force that's anchoring the moon towards the Earth. Another way of comparing this is if you've ever been on those swing rides at the amusement park, right? You can think of gravity as that rope that's holding you from flying off of the ride, right? So gravity is pulling towards the center. At the same time gravity is pulling towards the center, inertia, right? If you remember from Newton's first law, object's resistance to change, inertia is causing that object to want to move off straight in the direction that it's moving, right? So the moon, as it's moving sideways with Earth, wants to move off straight. It wants to go flying off, just like someone, if gravity were to disappear and this rope were to break, would go flying off the ride. The moon would go flying off into outer space if not for this centripetal gravity force pulling it inward. So that kind of explains Maribel's explanation. There is gravity. It is pulling the moon towards the Earth, but inertia is preventing it from falling down. It's keeping it moving sideways, constantly in a circle. Really two forces there. If Earth were to disappear and there were no more gravitational force, of course the moon, as we said, inertia would cause it to move straight off into space. Alright, that leaves us to our final prompt. This is falling through the Earth. And I thought I'd show you this clip because I think it shows a much better visual than I could actually explain in words. So we'll watch this.
Hey there, welcome to Life Noggin. You know what would be really cool? If we had a hole that traveled straight through the Earth from pole to pole. I mean, you can go from seeing Santa to seeing some penguins in Antarctica in no time at all. But anyway, you might be wondering, how long would a trip like that actually take? Well, let's start off with some simplifications. Firstly, we're going to assume that the Earth has the same density everywhere, is a perfectly symmetric sphere, and the hole has no air in it, because otherwise the air resistance will cause you to reach terminal velocity, meaning your speed will eventually plateau. So with those assumptions out of the way, we're ready to begin. Let's suppose you're standing next to this super dangerous hole and fall in. And like you'd normally experience if you fell into any hole, you're going to accelerate down. But how much you accelerate depends on how far you are in the hole. See, when you're at the top of the hole, the entire Earth is below you, so you'll experience the same gravitational acceleration as you normally would, 9.8 meters per second squared, and you'll start to speed up as you fall. But then things change. Now you are inside the hole, so some of the Earth is above you and some of it is below you. And this means that the gravitational forces are both pulling you up as well as pulling you down. So your acceleration is going to change. Luckily for us, there's a simple trick that we can make use of to figure out how much. Let's pretend you are inside a spherical shell with a uniform density. In here, no matter where you are, the gravitational forces from every part of that shell will cancel out. To actually prove this, you need to know a super cool thing called calculus and add up the forces from every single tiny portion of the shell. But to keep this video from getting too math heavy, just trust me that it works. Now, as you are falling towards the center, the parts further from the center than you are form a spherical shell. And we just said that all of the gravitational forces from that shell will cancel out. So this means that we can simply pretend that that part of the Earth isn't there. And, instead, you are standing on the surface of a smaller Earth. So, as you fall, the Earth basically gets smaller and smaller, and your downward acceleration decreases. And once you reach the center, you won't experience any acceleration at all. But remember, you are still falling down pretty quickly, so you'll zoom right past the center towards the other side. And from there, instead of the Earth shrinking, it's getting larger and larger as you fall down, since you are now moving away from the Earth's center. And with all that Earth above you, the acceleration will flip directions and now will be pointing up. But since you are still traveling down, this means your velocity will start to slow, eventually reaching zero when you get to the other side of the hole. And if you don't jump out, you'll fall right back in and oscillate back and forth in the hole, forever. I don't know about you, but I definitely have better things to do with my time, like make these amazing videos. But assuming you only travel through the hole once, using some physics, we'll find that this whole trip will take you around 42 minutes. Not too shabby. So what do you think the coolest way to travel across the world?
Alright, so as you can see, falling through the Earth isn't as simple as just falling and ending up on the other side. You end up on a longer journey than you'd hope. Go ahead and update your prompts now with your new thinking. Do that in a different color. And if you have any further questions or ideas, feel free to bring them up in class. Have a great day. Bye.